Come on, we will start with the derivation of the torque acting on a rectangular coil. Fine. So one rectangular coil has been given to you. Fine. Here we have taken this general case. Fine. So suppose you can see here. Suppose the coil is given to you like this. Fine. A rectangular coil. First you need to find out what is a direction of an area vector. Suppose the current is in the clockwise direction. So you have to put your fingers in the direction of current. Find the thumb indicate the direction of area vector. So here the area is inside the plane of paper. If it is like this, area is in the upward direction, means it is in the up direction or perpendicular to the plane of paper outside. Fine. So it would be like this. Now here we are not taking this case. Suppose that if the coil is kept like this in an uniform magnetic field. Fine. So what is the direction? Suppose I say that B is along x-axis. So area vector would be like this. Fine, inside the plane of paper, and B is like this. So what is an angle between B and A? 90 degree. Fine, but we are not taking this case. We are taking a rectangular coil at some angle. That means B and A are having some angle theta. Fine. In this case, what is an angle between B and A? 90 degree. But we are taking a sub-generalized case. We are changing the cross section of the a rectangular coil in such a way that the area makes an angle theta with the magnetic field. Now you can see that the uniform magnetic field which is produced by the north-south electromagnets, fine, it is along x-axis, and area vector makes an angle theta with magnetic field B which is along x-axis. Fine. Now you can see that we have taken the current in the clockwise direction. Now we need to find out what is the torque acting on this rectangular coil. Fine. Now you can see that this is a rectangular coil which carries the current I. You can take any one cross section. Suppose I say PQ. Fine, from here this line, that is PQ. Fine, you can take any current element. Fine, IB, and we need to find out what is the force on this current element. Fine, due to this magnetic field. Fine. Now you know that we require to use the Fleming left hand rule to find out the direction of force. Fine, you know this is the direction of current, this indicates the direction of magnetic field, this indicates the direction of force. Fine. So you need to find out how to find out the magnetic field. Force is along upward direction, that is along y-axis. Fine, you can see that this is along x-axis. Fine, current is given in this direction, so we need to find out the direction of force. Fine, so at this point you can see that B is in this direction, current is in this direction. So B is in the upward, force is in the upward direction, yes or no? So at this point the force is in the upward direction. So similarly here, since this is an opposite point to this, fine, so definitely when this force is in the upward direction, fine, so for this point the force would be in the downward direction. Yes, fine, but you can see that this force and this force are having the same direction, means their line of action are same. You can say they are collinear. Fine, what is the magnitude of the force first? Fine, so we say that the magnitude of the force, fine, for the first force we say IB cross P. Okay, IB cross B, which is along which direction? It is along positive y direction. And what would be the direction of any element along minus IB, because this is plus IB, so this becomes minus IB. So this would be what? Minus IB cross B. Fine. And which direction according to the Fleming left hand rule? It is in the negative y direction. Now this force, that is F1 and F1 dash, both are equal and opposite. Fine, you can see that this is plus IB cross B and this is minus IL cross B. Fine, both have the same magnitude, directions are opposite but with the different line of action. This is IB cross I minus IB cross B, because this is length is P. Fine. So you can see that both have the same magnitude, direction are opposite, this is positive, this is negative, with the same line of action. You can say both are collinear, so they cancels each other's effect. Fine. Now we will see that what would be the force force on this line elements. Right. So you know that for this point you can consider any line element from this. Fine. Or you can say current element, that is IL, which is along which direction? This is a negative y direction. This direction is what? Negative y direction. Fine. So we know that the current is what? Current is, I can say that it is ILJ. It is in the negative y direction. Fine. And magnetic field is along which direction? X direction. So using the vector product, fine, you can find out the directions, fine, in the using the cross product also. The force on any current element, that is QR, means this line, fine, would be what? You can see that minus ILJ, because this is along negative y direction, minus ILJ cross BI, fine, because magnetic field is along x axis. So what would be the value of the force F2? That is minus ILB, you know, J cross I is minus K, so minus will become plus. So this indicates that this force, that is F2, is in which direction? Positive Z direction, fine. Similarly, for any force, any line element from this part having the force F2 dash, and this F2 dash we can calculate using the mathematical formula, that is ILJ, because you know ILJ means what? Current is in which direction? Positive y direction. You can see here magnetic field is in x direction. So can I write ILJ? Fine, current element is along which direction? Positive y. Magnetic field is along which direction? Positive x. So BIL, J cross I. What is J cross I? J cross I is minus K. So this indicate what? That this force, that is F2 dash, is in which direction? Minus Z direction. So from the mathematical equation, we calculate that this force is in which direction? Negative Z direction. This force is in which direction? Positive Z direction. Fine. One is in positive and another is in negative. You can see here. Fine. One is positive Z direction, another is negative Z direction. But we will see that using the Fleming left hand rule, this force may be equal and opposite, but they are non-collinear. Fine. When these forces are non-collinear, you know that they constitute couple, and effect of the couple is torque. And what is an effect of the torque? Rotation of this rectangular coil. Fine. First we will see where is F2 dash. Why the line of action both are different? You can use again the Fleming left hand rule. Fine. You can see that here the current is in this direction. Fine. This is the current direction. This is the magnetic field direction. So in the plane of paper, you can put like this. You can see that the current is in this direction, magnetic field is in this direction, where the force will come in the downward direction. Fine. So this force is in this direction. So definitely the opposite point will have the force in the upward direction using the Fleming left hand rule. Fine. So what will happen? They constitute couple, and effect of the couple is torque. And due to this, what will happen? There is a rotation of this coil. When this coil get rotated, you can see that this point M1 will reach at this point, that is at point P, means M1 coincides with P and N1 coincides with R. You can see here. Fine. So this point will reach here. So this would be the condition, and this point will reach here. So this would be the condition. And what is the perpendicular distance between two forces? See these two forces. The line of action of this force is this, and the line of action of this force is this. So this will behave as a perpendicular distance between the two forces. And you know that we need to find out the perpendicular distance between two forces. Fine. Now you can see that here we have seen this point is O. So this point is O. Here you can see here M1 coincides with P, M1 coincides with P, N1 coincides with R, N1 coincides with R, but we need to find out Mn because this is a perpendicular distance. Then what is this value? This, since this is B, breadth, so this will be also B, and center point is O, so this is B by 2 and this is B by 2, so we have written this is B by 2 and this is B by 2. Now you can say that theta is an angle between B and A. Here you can see that B and A has an angle theta, but you can see that this part is totally 90. So if this is theta, this is 90 minus theta. Fine. If I take this triangle, this is 90 minus theta, this is 90 degree here. So what would be this? This is theta. If I consider this triangle, that is O and N1, what is sine theta? Opposite side upon hypotenuse. I have taken opposite side as x. Fine. So what is this? See, opposite side, that is x. Fine. This is x upon B by 2. Fine. So this would be what? We have find out x is written as ON here. So ON is equal to B by 2 sine theta. Fine. Can we write like this? Sine theta is equal to, see, I will show you here. Sine theta is equal to x, fine, which we have written as ON upon B by 2. So can I write B by 2 sine theta is your x, but we need to find out 2x. So if I multiply 2 on both the side, can I say this 2x is ultimately what? It is mn only, and we need to find out mn only. So mn becomes what? Ultimately it becomes, this 2 goes away, b sine theta. Fine, that is only the perpendicular distance. So just put this value here. You know, torque is magnitude of any one of these forces into perpendicular distance. Magnitude I can write BIL. Fine, I have written BIL. Perpendicular distance from the geometry we get b sine theta. Fine, we know that length into breadth is an area of the rectangular coil. It is replaced as A. If the coil has n turns, we multiplied with the factor n here. Fine, but you can see that this physical quantity NIA we represent as magnetic moment. Fine, how to find out the direction of magnetic moment? That can be explained. Fine, by direction of the current. You can say if the current is in the clockwise direction, fine, you have to put the direction in the, you have to put the finger in the direction of current. Fine, then thumb indicate the direction of magnetic moment. So here the magnetic moment would be in the direction which is perpendicular to plane and inside. Fine, so this would be the direction. Again you have to use, how to find out? You have to put the fingers in the direction of the current and the thumb indicate the direction of magnetic moment. So if I replace I and A by small m, that is a magnetic moment, then the torque becomes mb sine theta. Therefore what is torque? Torque is m cross b. So vector wise we write m cross b. Now we know that the torque is maximum if and only if sine theta is 1 or sine theta is 90 degree. Fine, and that maximum torque becomes b now. Fine, and when the torque becomes 0, when sine theta is 0 or it is 180 degree. Fine, so this would be the torque which is acting on a rectangular coil when it is placed in an uniform magnetic field. I hope you understand.